Oh, did anybody not get their test back? Did I miss somebody? Oh, I thought I did. Are you Mario? Yes. Okay. All right. Everybody else, yeah. Did they start you up? I did. All right, guys. So you're never gonna believe what we're gonna do. We're gonna finish section 1-2. We're gonna get into section 3-1, and then we're gonna call it a day. That is the plan. Let's see how it goes. So, one of the biggest things in mathematics, oh, go ahead.
So homework for 2.3 is due.
2.3 was due the day of the test. Yeah, 1.2 is due the day of the next test, yes?
Yeah.
I'll have problems from 1-2 on the next test.
Yeah.
So 2-1, 2-2, 2-3, 1-1 was due last time. Does that mean you can't turn it in? If you haven't turned it in yet, can you still turn it in? Yes. It's just late, that's all. The later something is, the worse.
So the 1.2 is the next one.
Yes, that's where we're gonna start.
It's due
The day of the next test.
Day of the next test.
Yeah, off the top of my head, I don't know when the next test is. Yeah. All right. So we start. One of the most fundamental things about math is finding a pattern, right? We find a pattern, we develop a process, and then we use the process. One of the hardest things for math students to understand is they'll apply a process and they'll forget why it works. And then it kind of goes into this feeling like, I just do what these people tell me to do. I don't know how you guys feel about a lot of the math you've taken, but a lot of times students just feel like, well, this guy said to do this shit, so I'm gonna do this shit and make him happy. That's such a wrong way to look at math. If you're doing shit you don't know why it works, then you should be like, dude, tell me why this works. And they explain it and they're like, that didn't make any sense. That's their job. It's my job. That's your future job, is to explain in multiple ways so that it makes the most sense to the most people. Yes? That's one reason I love this job, is because I love that challenge. I miss teaching Math 88, which is where I taught 2 minus 7, for example. Yes? Because these are older students who have seen this shit over and over, and I have to come up with a way that's gonna connect with people that they maybe haven't seen yet. You guys kind of with me? And that challenge is awesome. So a lot of my grad school friends, they're like, how the hell can you teach freaking 2 minus 7, Jeff? That must drive you crazy. I'm like, 2 minus 7 is easy to you and me. It ain't to everybody. So I gotta come up with something that's gonna connect. Okay, enough. So let me ask you this. Finding a pattern in things, the most basic problem you would see based on finding a pattern is this kind of problem. Not sure what happened over there. What kind of problem is this? What is it implying that it means, right? So, yes. So, sorry. There's something happening outside. It's freaking. Nothing maybe. It's asking you what are the next 2 terms in the sequence, right? So that's a sequence of numbers. There's some generating pattern behind it. Does it make sense when I say generating? There's a way to generate the next sequence number, right? The most obvious answer for this is like you said. You already said, what's the algorithm for finding the next? Add 3. Now what's funny is, I will make a problem like this, and I'll have an idea of what I want the next answer to be, and then somebody else will see a different pattern than what I intended. You guys kind of with? In fact, if I would have just put 1, 4, if I would have just put this, So, real quick, before I move on, what's the next number? Holy shit, because I keep adding 3, so if I add 3 and I add 3, I get, holy shit, okay. If I would have just put 1, 4, it could be 7, 10, right? Does anybody else know what else it could be? Do it again. Why 16? Yeah, maybe I keep multiplying by 4, yeah. So maybe the next number is 16. Does anyone have anything else it could be? Oops. If not, it's okay. That's fine. There are some other things. So, for example, it could be maybe I multiply by 3 and add 1. Do you see what I mean? What's 3 times 1? 3 plus 1 is 4. So what's 4 times 3? 12 plus 1 is 13. So maybe the next thing is 13. Do you understand what I'm trying to say? I'm not going to give you a problem like that where I know for sure there's not enough information. But even, I don't know if you guys are really with me, even if I think I give enough information to make people think the way I thought, maybe I left it open to other things. So I'm just trying to say, as long as you show me, now if I gave you this problem and you put plus 3 like that, that's your work. Tears of joy, yes? You gotta show me your thought process. I'm gonna ask these people to move on because for some reason it's really bad. I'll do that. Yeah, thanks. That's okay. Sure. No worries. I don't know why it is. Now they're gonna move like 3 feet. Okay. Okay. What about, let's do another example of a what do you got, Jeff? Sequence. There's more than one way to get the next element that I'm thinking about. So what do you try? It could be adding the same thing. It's definitely not adding the same thing. It could be multiplying the same. It's not multiplying. It could be adding by numbers that themselves go in a pattern. So what do you add to 1 to get to 4? 3. What do you add to 4 to get to 9? 5. What do you add to 9 to 16? 7. Do you see that? Does anyone else notice anything about the numbers themselves? They're all what kind of numbers? 1, 4, 9, 16.
Square roots.
They're squares. They can be square rooted. They're squares. So let's see if we get the same number the other way too. So does everybody see? This is plus 3, plus 5, plus 7. What do I keep doing? Adding the next odd number. So what would I add here? 11. So that would be 36. And then I add 13, and that would be, are these still squares? So that is trippy. I know you guys know square numbers. I know you do. But when I wrote that down, I didn't expect people to, because I knew you guys would start going 1, 4. You weren't going to step back and look at the whole list and go, oh, they're squares. You did though. That's neat. I like that. Is everybody with me? So it's okay if you didn't notice they were squares right off the bat. But if we know square numbers, did anyone know that the square numbers are all separated by the next odd number? Does anyone see that that's kind of nifty? Does anyone care? It's okay if you don't care that much, because you're like, oh, that's interesting, but okay. Why, this is going to sound stupid, but why do we call those square numbers? Multiply them by themselves, right? So a number multiplied by itself to make this, right? So watch this. 1 is represented like this. 4 is a little square, yes? How many did I add to this picture to get to this picture? 3. Now watch, if I just start with this foundation, and I add dots around the corner to make it a square, how many did I just add? All right, do you guys see that? So you have a like a computational way to see the pattern and apply it, and then you have a geometric way to see the same pattern, and the geometric way is like, well, of course you call them square numbers. They set up a freaking square. You guys with me? Okay. Now again, what's interesting about mathematics, and you guys know this, most of you guys are going to become teachers, or you want to become teachers. You yourself have lived through, some of you might be doing it right now, a situation like, all right, what good is this shit? So you're going to have students that might feel the same way. But the more you're able to play with the numbers like this, the more advanced mathematics you can understand. The more general everyday shit you can do. Because you've got this ability to play with things both computationally, visually, yes. So as a teacher, you've got to instill in your students an appreciation for and an understanding of these different ways to look at it. You're setting a foundation for their whole freaking future, not to make you, especially getting really young students. When can you turn a student off to math? Immediately, right? So to me, it would be really neat to teach elementary school. I told you guys I'm not an elementary teacher. I never have been, so I feel a little bit like I want to, but it'd be neat. But it also, there's a lot of, not to make you worry, there's a little bit of pressure on you because you're setting up foundations for everything this person's going to do. This little human, you're setting their foundations up. Look, yeah. What else can I talk about too much? What about this one? That one's a little more straightforward. What's the first two things you check? What's the most fundamental way to make a sequence of numbers? You keep adding the same thing, or you keep multiplying. So you rule those out first. If neither one of those work, then you go, okay, what other kind of weird shit is this guy giving me? What's happening on this problem? Yeah, every other one's negative. Multiply by -3. That would make the sign change every other time, right? Okay. Or the sign negative every other time. So I'm multiplying by -3, -3, -3. So what will the next number be? Hmm? 81. And then I want to multiply by -3 again. 243. Kick ass. Kick ass. Okay. So as long as you show me work on this kind of problem, you could actually have a different answer than what's on my P. Because maybe you noticed something I didn't even think of. So as long as you show me the work, I'll know, cool, I didn't even think of it. If you just plot numbers down, I might miss what you saw. Does that make sense? That's why it's so important to show your work. Okay. What about this one? If you know this one, don't say anything. Let everybody think about it for a second. Jeff, do you know it? I just started counting. That's good, Jeff. All right, don't say anything yet. I want to share something. It's really weird to me. Like, you told a joke and said, stop me if you've heard this one, right? Have you ever done that kind of thing? I got a joke. Have you ever heard this? Stop me if you've heard it, right? I understand that in this room, I am the ultimate math geek. So it's always funny to me when I'm like, tell me if you've heard this one, of this math sequence. But it's possible some of you guys have seen this before. Without telling me anything about it, how many of you guys have seen this before? You seen it? Okay. You seen it? Okay. You seen it? Sweet. Okay. Now to one of you three, do you know the name of it? Or do you know the generation of it? How do you get the next term? Say again. Oh, so how do you get the next term? How do you do that?
So you do 1 plus 1 is 2.
Good?
And then 1 plus 2 is equal to 3. And then 2 plus 3 is equal to 5. And then 3 plus 5 is equal to 8. 5 plus 2 just add the...
Yeah, so what's the next number? 21. And what's the next number? Now, Do any of the other two of you know the name of this guy? Okay. Fibonacci. Fibonacci. Have fun with that. So Fibonacci sequence. There's really dumb math jokes like Fibonacci, where you eat one nacho, and you eat one nacho, and then you eat two nachos, and then you eat three nachos. I told you it was dumb. You guys see that though? Now, here's what's really tricky. Have you guys ever gotten a note card, a little note card you can put notes on for a test? You with me? Does anyone know the size of those note cards? 3 by 5 or 5 by 8. 3 by 5, 5 by 8. So, here's what's really exceptionally tricky. Do any of you have an alarm that goes off like, You guys know about those alarms, even if you don't have them. You also have certain harmonies that sound like certain notes that go well together. Have you ever listened to music? You know, there's notes that go well together, notes that don't. I could spend the entire semester talking about the sequence, and I will not, but I want to point out a couple things. If I have numbers, frequencies that are in this sequence, when I put them together, they sound good. So when I want an alarm that'll wake me up, I just use frequencies that aren't elements of the sequence, or don't have the same kind of generation to them. Things that follow this, like the 5 by 8 card, are aesthetically pleasing to humans. So do you see what I mean? Like the sounds are pleasing if they're elements of this sequence. They're generated the same way the sequence was. And they're not pleasing if they aren't. Visually, things are pleasing if they're kind of elements of this, and they're not if they're not. Are you guys? That's trippy as shit. Because this is just like some math dude in the ancient times when they had nothing. They're like, I got a candle and a paper and a thing. Okay, 1 + 1 is 2. This is neat. You know, they just wrote it, just played with numbers. But then it has everything to do with, notice how the sequence is building on itself? Isn't that what every animal, every nature, every plant builds on itself as it grows? And that's why you see this in the number of limbs at a certain height on a tree will follow this if somebody hasn't chopped the limbs off and so forth. Okay, I'm going to stop there because I could go on. And I could tell some of you guys are like, okay, did we get it? You like this shit? Okay. Anyway, so I'm going to try to stick, when I give you a quiz or a test, I'm not going to give you like an exceptionally freaky sequence. I'm going to give you something that's not too crazy. This is a little bit crazy if you've never seen this before and they just give it to you. That's kind of neat. Because not many people would stop and think, oh, I just add 2. Right? Are you guys with me? Quick question, has anybody ever gone to Canada? Or has anyone ever gone to any other country, actually? They use metric there, yeah. So what's neat is, if I'm going 80 kilometers an hour, that's roughly 50 miles an hour. Because the conversion between miles and kilometers is roughly the multiplier that kind of happens between these. Okay, that didn't sound very good. So you could use this as a shortcut. And I did. I was recently in Canada. I was driving through Nova Scotia. I'm like, oh, I know that. Yeah, how fast am I going? Oh, yeah. All right, doesn't take much. Okay. Blah, 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 blah. Oh, good. Okay, that's that one. Well, next. So one thing we just did is look for a pattern. You make this official. Another thing we can do is make a list. So let me start with a really simple example. I have 2 numbers that multiply, add to 12 and multiply to 32. Now, even if you get the answer very quickly, I want you to realize what you've done to get there. So they have to add to 12, and they have to multiply to be 32. So how would making the list help? Has somebody already figured out the answer? Okay, good. So can somebody give me just a random two numbers that add to 12? Two numbers that add to 12. 6 and 6. Yes, 6 and 6. How do you know that's not the answer to the problem? Because they don't also do what? Multiply to 32. So I need two numbers that add to 12 and multiply to 32. So do you see how making a list helps? In fact, I should say two whole numbers here. So now, if you just make a list, okay, 6 plus 6 is 12, but it doesn't work for this guy. Nope. 7 plus 5 is 12, but 7 times 5 is 35. Nope. You see what I mean? So this is astonishing, but this is making a list. So this is an official method to solving a problem, is you make a list and you just check. This is a classic example of making a list. If you've ever done any algebra where we had to factor stuff, you had to find two numbers that multiply the last two, and they have to also add to be the middle two. Does that sound at all familiar to anybody? So that's exactly what it is. It's just a number game, just a puzzle. So what is the answer? 8 and 4. If I just kept going, 8 plus 4 is 12. 8 times 4 is 32. Sweet. Okay. So let's do a slightly more complicated example of making a list. All right, this is a little more complicated. I have 6 baseball teams. In this league, we are very boring people, and we name the teams A through F. Very exciting. So there's Team A, Team B, Team C, blah, blah, blah. Okay. Each team plays the other teams twice. Does that make sense? So like Team A plays Team B twice. Team A plays Team C twice. You guys with me? How many total games are played? And I want to point this out. I can't remember if I said this, and if I didn't, I apologize, but these word problems can really frustrate and cause anxiety. Is that true? If you just show me the work, I think I said this. The work is the bulk of the points I give. The answer is almost extra. Because the most important thing for me to see is, how are you thinking about this problem? Are you using a strategy that will work? Are you using the strategy correctly? If you get the answer, it's almost like, oh, okay, good. You guys with me? It's like having a donut with stuff on it, and then, oh, it can also put sprinkles. I mean, did it get that much better? No. You with me? So you get the answers like the little sprinkles. I'm okay if you eat sprinkles or not. So, does anyone have a clue how to even start this? Can you guess and check? You can? How do you do that? I like it that you were like, I'm sure there's a way. There's gotta be a way. I know somebody would try. There's no way to guess and check this, right? How would you check it? Because I don't know what the answer is supposed to. I have no way to know the answer, anything. So there's no way for me to check. Does that make sense? There's just a number answer that I could only get to a certain way. What kind of list could you make? I sort of started it just a second ago. If you're listening. What kind of list could you make?
You could do like the letters, so like A plays
Yeah.
B, A plays C. And
Yeah. So focus on Team A. Focus on Team A. Who do they play? B, C, D, E, F. And how many times do they play each of those? How many? Well, they play each of those twice. So how many games do we have so far? You guys know how to go from there. Are you guys at all with me? Alright, listen. Do you agree? In fact, I said this earlier just to explain the idea. A plays B twice, yes? Who else does A play? C, who else does A play? D, who else does A play? E, who else? F. A plays each of those teams twice. How many games do we have so far? How many games do we have so far if they play each of those teams twice? 10. 10 games so far. What do you think we're going to do now? I started from A's perspective. Now I'm going to go to B's perspective. So one huge thing about making a list is being systematic in how you compose it so you don't lose anybody. If you just start going, well, A's going to play C and D's going to play F, and holy shit, how can you be sure you got everybody? So you have to be a little systematic in how you set it up. Okay. So from B's perspective, what do you have to be careful about? Who has B already played? So then who's B going to play? C? It's already played A. You see what I mean? Have we already taken care of the A-B game? That's happened twice already, right? So we got 10 games so far. B's going to play C. B's going to play D, E, F. How many games is that total, considering they play everybody twice? That's 8. Now you can combine make a list with see a pattern. From A's perspective, there's 10 games. From B's perspective, there's 8 because I didn't have to double count A, B. So what do you think from C's perspective there's going to be? 10 from A's perspective. 8 more from B's perspective, yes? How many more from C's perspective? What would you guess? And let's verify. C's going to play D, E, F. Why don't I have A and B? I already have the AC game. I already have the BC game. Why would I do it again? They're only supposed to go twice, yes? And sure enough, that's 2, 4, 6. So what about from D's perspective? 4. What about from E's perspective? 2. And then F can't play himself, so I don't even need an F. F's already played everybody, yes? I guess all... Now real quick, you all know I ain't going to give you this problem. I ain't even going to give a problem that's like this a lot. What's more important is, what was it about the problem that told me I should try to make a list? I can't guess and check because there's not enough parameters to live within. I have to look at it as, how do I list all the games that I could play in a systematic way? Okay, let's make a list. So how many total games? 30. I think, right? 6, 20, 30, yeah. Okay. So you have got to stop looking at this as, and I don't blame you for this. You have to stop thinking about this like, I didn't see a problem like this. I don't get the answer. No, just start doing something. Even if you didn't do exactly what I did, I will still give you some points if there was some logic behind what you're trying to do. Does that make sense? This is not the only way to do this problem. This is probably the best way to do this problem. It's not the only way. Then comes one of my favorite approaches. So the most basic example of this I can give you, solve a simpler problem. This happens all the time with, you're working with these funky ass numbers. You're like, I don't know what to do with these numbers. So for example, here's a good example of this. Let's say someone is traveling at 154,967,211 millimeters per hour. We excited so far? How long, good Lord, Jeff, how long for them to go 3 trillion, or 3 billion millimeters? Does everybody agree that that is a heinous kind of crime? And the only reason it's heinous is because of the numbers. Has anyone ever seen a problem like this anytime in your whole life? Some of you guys are like, if I did, I blacked it out. So here's the most basic way to use this idea. Substitute the ugly ass numbers with beautiful round numbers. Suppose someone's going, in fact, even substitute the stupid units. Do you all agree with me that the numbers don't tell me what to do? There's a way to do this, but the numbers aren't what telling me. They're actually getting in my way, so my brain can't tell what to do. Do I divide? Do I multiply? Do I add them? What the shit? So, what if I was traveling? So simpler problem. My God, Jeff, what letter is this? I don't know. Simpler problem. What if I'm going 10 miles per hour? How long to go 20 miles? I've made better units and I've made better numbers. Do you see how it doesn't change the underlying mathematics required? You guys see that? What if I would have said 50 and 80 and what? I mean, the same math would happen. If the units change, the math doesn't change. So how do I figure that out? How long will it take me to go 20 miles? 2 hours. Right. What did you do? How did you get 2? What do you actually do with 10 and 20? We took the distance I want to go, and you divided by the speed you're going. Yes? Do the same shit to this now, right? Soon have a calculator. Does anyone, all right, you guys see what I'm trying to tell you? There's not a damn thing wrong with this. I'm going to show you an algebra example in a minute. Something that I try to always show my students whenever I teach them word problems for the first time. Like, I was about to say real word problems, but algebra word problems. We have to develop your own equation and blah, blah, blah. So can somebody just articulate for me? I don't want the answer. How are you going to solve the original problem? What are you going to actually plug into your calculator? So we figured out right here, I take the distance I want to go, divide out how fast I'm going. So what am I going to do? Divide. Okay. I have to gauge. So as a teacher right now, I'm trying to gauge. Are people shy? Do people really not understand me? How many people really don't have a clue what the shit's going on? Anybody? Alright, so everybody has a clue what's going on. So what do I do? What do I divide? Yeah, how far I want to go. How far do I want to go? 3 billion. That's fine. I made the exact same mistake earlier. 3 billion divided by that, right? I mean, your brain latched on to these numbers. Most of you guys knew the answer was 2, and if I really pushed you without saying anything, you wouldn't even be able to tell me why necessarily. Like, it was 2. Because your brain just saw 10 and 20, and you went, oh, in 2 hours. So you do the exact same shit with the uglier numbers, but this time you plug it into the damn calculator, because my brain can't do that. I think it's going to roughly be, I'm going to try to guess this. It's going to roughly be 18.9. What is it?
19.
19.3. I'm sorry.
Well, 0.4.
I'm even worse. I'll retire. It's not that bad, right? I'll be alright. It was pretty off, I'm sorry. So if I just take this, divided by this, I'll see how many hours it's gonna take. Does anyone see what just happened? If you have a problem, don't care what it is, and the numbers are gross, replace them. Replace them with nice, small, whole numbers. Your brain will go, oh, I see. And then you go, oh, thanks, brain. Now do the same shit with the uglier numbers. That is a perfect example of solve a simpler problem. Yes? Okay. So, here, I'm going to push one up here. Another solve a simpler problem example. Let's say there's a TV on sale for $896.11 after a 22% discount. Is everybody with me? So the question is, what was the price before the discount? Now, in terms of where we are in this class, this is a very advanced problem. But I just want to reach back to a standard kind of algebra problem you could have gotten in the past. And I want to show you how to use a simpler problem to solve it. Wait, can you let me? The most common mistake I got, can somebody tell me why this is a mistake? And some of you guys might be doing this right now. Why can't I take 22% of $896.11 and then add it on top of that? Real quick, even if you didn't think that, can you see the logic in that? Even though it's wrong, there is a logic to it. Let me say this again. This is wrong, but you can see the logic to it. If I take 22% of $896.11 and add it to $896.11, do you see the logic behind it? But some of you guys are like, yeah, why is that wrong? How did I get to $896.11? What did I take 22% of? A bigger number, yes? Really, somebody with me. That's how I got to that, was 22% of a bigger number and I subtracted it. So how could 22% of that smaller number get me all the way back to where I started? Does that make sense? I'll do it one more time, because this is kind of, if I want to take a discount, I take the percentage of the original. In this case, that's a bigger number, correct? And that, when I do 20% of the bigger number, it's more than 22% of the 896, the smaller number. So there's no way adding that amount back on can ever get me back to where I started. That's backwards. I didn't take 20% of the 896, it's 22% of the 11. Now, here's a simpler problem. You with me? Simpler problem. They come. And I'm not, let me do this. What would make this a simpler problem if I knew what the original cost was? Say original is $1,000, yes? And I'm going to keep the percentage the same, 22% off. Can you guys tell me in that simpler problem what the sale price will be? It was $1,000 last week. This week they put a 22% off discount, right? Can you figure out what the new price is? If you're not sure, then you could be getting taken advantage of, because there have been specific instances where stores have been found to be misapplying percentage discount on purpose, because they knew not a damn person would double check. Because not enough of us know math. You guys with me? This has been recorded. This is a known thing. That's why I want more people to know math. So we can stop getting taken advantage of. Does anyone know how to do that simpler problem? It's $1,000, 22% off. What do I do? How do you calculate how much money to take off?
You would multiply the 1,000 into 22%, and you subtract
Yeah,
that
so if I
number.
first figure out what is 22% of 1,000,
Which is 220.
that'll tell me how much money to take off. And then I'm gonna take 1,000 minus that, yes? So what is 22% of 1,000? Well, what is 22%? Again, this is a little early in our class for this, and I almost don't care, because you all have worked with percentages at some point. Does anyone know how to make a percentage into a decimal? Because do you know what percent means? Per cent. And when I say cent, what's the first thing that comes to your mind besides something smell?
Century.
Say again?
Century.
Century? The dude from the movie? Got all
Century,
black
like
and
100
people's
years.
Yeah. Cents. How many cents in a dollar? 100. So cent comes from centum, which is Latin for 100. Per cent literally means out of 100. Yes? So if I have 22%, what's 22 out of 100? 0.22. That is the actual number. So 0.22. What does of mean? Oh shit. If every bag has 2 apples in it, and I have 5 of those bags, how many apples do I have? Every bag has 2 apples. I have 5 of those bags. How many apples do I have? 10. Of means multiply. So 22% of 1,000 is 0.22 times 1,000. What's that? 220. So then you take 220 away from 1,000.
780.
Yeah, 70. Okay, now I'm gonna stop for a minute. Okay, I love you guys. We're doing okay. What part of this problem did I make up a number for that we didn't know in the original? Yeah, we didn't know the 1,000, correct? Okay, now listen, this is huge. We don't know what the original price was. So to solve the problem that it was, that I made a simple problem out of, what would we call the original price? We don't know what it is, so we call it X. So watch, this is almost too good to believe. If you just take what you did for the simpler problem and go, okay, we did 22% of the original, yes? You with me? We did 22% of the original. We don't know what it is, so 22% of X. And then what do we do? So replace this with X, replace this with X. We took what we got and we subtracted it from the original, yes? I really want you guys with me. I made up that $1,000, didn't I? Completely legal to do that shit because I'm trying to let my brain see the logic. To solve a problem, you can make shit up in the middle of it, and I don't care, as long as it helps you see the logic. So I made that number up, yes? Because then it's a little bit easier. Oh, okay, this is just I go to the store and I want to know how much it's going to cost. So now wherever I see 1,000, I could put X, because I didn't know what the shit it was. But my brain could latch on to this easier, and now I can go, okay, brain, now you showed me what to do with that funky X. So remind me, once we did this, what did we do with this? We subtracted it from the original, yes? So we subtract this from the original. And what do we get? What was this? No? The sale price. And what's the sale price in the harder problem? Now, I'm going to stop there for the moment. I mean, now you could solve that equation. Right? Does anyone know what a whole X minus 0.22X is? What's a buck minus 22 cents? What's $1 minus 22 cents? 78 cents. So that would be 0.78x, and you could divide by 0.78. At this point, I'm not too nonplussed about that. I don't think I've ever used the word nonplussed in a sentence before. You think, would you? You guys, listen, I'm not going to give you this kind of problem. It's a really good example of in your own math experience where you could have used this idea of a simple problem. And when I was allowed to teach algebra, which we're not allowed to do anymore in California community colleges, that's how I would teach word problems. Is I would show them, hey, just make up numbers for the thing you don't know, and then see what you do. See what your brain does. Your brain will do it. Go, okay, I got it, brain. And then do the shit with the X, the thing you don't know. Okay. I'll stop. I'm sorry. Bum. Oh, going this way. All right. So I want to talk a little bit about section 3.1. I'm going to show you videos of little people, right? You guys missed them? You guys have any favorites? There's some shirts I see they're wearing. I'm like, I want that shirt. It's like a dinosaur shirt. I want that shirt. So we'll watch some of them so I can shut up for a little bit. Watch a little person work on some math. I just want to lay down some groundwork before you watch students working with this stuff. 3.1. This is the fundamentals of how to teach addition. It's part of it. It's the first thing. First main thing is addition. Next main thing you're not going to believe it is subtraction. What do you think is the most fundamental way to introduce the idea of addition to a little human? What way might they have already encountered by the time they get to your classroom? Candy? Yeah. So like Halloween, something, they're like, oh, I got 3 candy bars and this guy put 2 more in there, and now I got 1 and 5. Yeah, so they maybe didn't put a label on that, but they at least have a grounding in what it means and why it's useful. Yes? So, I like that. I have a bag of candy that's got little, all right, it doesn't matter. I'm going to use the same symbols. Oh yeah, that'll work. The little twisty dudes. Yeah, okay. So I got a little supposedly fun size Snickers bar, which really isn't fun. I got a little candy corn, and I got a little twisty dude. Yes? Are you guys with me at all? So this represents the idea of 3, and I'm going to call this set A. So this is bag A, right? That's what I got. And then my friend Mikey over here, he got whatever the hell candy that is, leave me alone, and whatever the hell candy that is. Okay. So if we pool our resources together, right? You're not going to believe this. This is Sept. If we put these in the same bag, then I'm going to have. Oh God, what is that even? I don't know. It's like a heart with a little issue at the inside. Okay. So what I do is illustrate. Addition of what specifically? So this, of course, captures the idea of 3. This, of course, captures the idea of 2. So then this captures the idea of 3 plus 2. Okay. Now, listen. Again, I've told you this once before. If somebody asks you, what did you do this morning in your class, in your math, or what did you do this afternoon in your math class? You're like, oh, we added 3 and 2. Okay. We're much more fundamental than that. We're talking about the fact that you could potentially be teaching little humans that have no freaking clue what the shit this is. They know how to use things. They talk about toys. They know this other guy next to him has more toys, right? So that'll lead to subtraction. How many more toys does he have? You guys got it with me? But this is like, if we put our toys together, how many toys do we have, right? Or let's go to the 7-Eleven, try to buy something that may be a little older. Like, I got $3, I got $2, right? Do we have enough money to get something? Nowadays, I don't even know. Okay. So to make this a little more formalized, well, first off, I'm going to call this set C. That's insane. Do you guys remember what this represents? Yes, the number of things in A plus the number of things in B equals the number of things in C. That's crazy sauce. Okay. And very quickly, that would be true, for example, even if, and by the way, what is this C really? Isn't this C A union B? So this would be the number of things in A union B. Will that always work though? That works in this example. Will that always work? If I have a set A and a set B, and I find their union, and there's 3 things in A and 2 things in B, will there always be 5 things in their union? That is a very weird question to ask. But so let me just show you an example where that doesn't work. What if A was, you can just make something up, Jeff, E, F, G, and B is W, F. What is A union B? No. E, F, G, W. And why would you write F twice, right? Do you see the issue? That would make it look like 2 plus 3 is 4, yes? Okay, I need you guys with me. So listen. You are always going to need to know much more than what you are currently teaching your student. Does that make any sense? Are you going to actually show this to your student if they're really young? Let me do this here. Look at this set. What the shit are you talking about? You have to understand this behind the scenes, though, because these are related to mistakes that they can make. You're not going to teach this, but you have to have it in mind as you teach them, so you can catch mistakes they make or whatever. Okay, maybe. Just like we saw earlier with the straws. You remember that, the kid with the straws? And that was a very heartbreaking thing. Right when he noticed, he's like, "I'm a failure." I felt so bad for the kid. Okay. So this only works. So let me make this more specific. If A and B are disjoint, sounds like I don't know grammar. Disjoint, that joint. But no, disjoint means they don't share anything. They're not joined in any way. If A and B are disjoint, these 2 sets are disjoint. Why? They don't share anything. If A and B are disjoint, and the number of things in A we call little a, the number of things in B we call little b, then A plus B equals the number of things in A union B. Oh my God, that's a lot of shit. So if they don't share anything, and there's little a amount of things in set A, and there's little b amount of things in set B, then little a plus little b is how many things are in their union. And we see an example of that where it worked here, because these 2 were disjoint. They didn't share elements. Now, I kind of want to share a story with you real quick about. I went to college. I wanted to teach algebra. I wanted to teach high school algebra. So are you with me? When I went to college, they said, "Oh, good. You want to teach high school algebra? Well, take calculus, get a math degree." And I thought, why the shit would I take? What do you mean? I just want to teach algebra in high school. You with me? You understand? I had to take the calculus to understand why I needed it, because as I went further, I'm like, oh, there's these more fundamental things underneath all of this base level stuff that we teach little kids, that if I didn't understand those things, I couldn't make the connections for them. I couldn't catch their mistakes. I don't know if you guys are with me. So again, I think you understand. You have to understand things at a much deeper level than you will ever show your students. Does that make sense? You have to. Okay. Does this make sense? This is basically just capturing very formally what we did here. And this, of course, is a counterexample when it's not disjoint, when they share something it doesn't work. Okay. With that in mind, though, as long as we have, for example, I could represent 3 plus 2 like this. Now, don't they share things? But in this case, what do the little circles represent? 3 things, 2 things. If I have 3 candies and I add 2 candies to it, of course I got 5 candies. Yes? You guys got it? So this is the what's called the Sept method of adding, but it's not written this way. It's much more visual than that. Okay. So let me see. Before I get there, and I know this looks like a bowling ball. Blah 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 blah. Oh yeah. So we'll get there later. Measurement model. Whenever you see them reference the measurement model, it's going to be a number line. So how could I use a number line to help illustrate 3 plus 2? What do you guys think? How to use a number line to illustrate 3 plus 2? And also, before I forget, this book does something a little funky. I kind of disagree, but it's a very fundamental thing about this book. It pretends like negatives don't exist. And I know in the curriculum, I think that's sort of true, but it just, there's later sections that redo everything we did in the earlier sections because later we know negative numbers. Is that, you guys kind of with me? So if I was going to draw a number line for a student at this level, where does it start? 0. Okay. How could I use a number line to illustrate 3 plus 2? By the time a student is looking at a number line, what do they know? They definitely know how to count, yes? So I just put some numbers down. So how would I use a number line to illustrate 3 plus 2? There's a few different ways to do it actually, but how would I do 3 plus 2 in a number line? Do it again.
Arrows.
Sure, arrows, okay. So how would you represent 3? Here. There's 3, yes? And what I normally do, and you don't have to do what I do because the book does something different, I do what's actually called counting on. That is a valid method of adding things, to be honest. And so if I go find 3 and then go 1, 2, I count on by 2, I see what the answer is, yes? The book shows, this is valid also. The book shows 3 plus 2 is 5, but to me, a younger student won't necessarily connect with that as well as counting on from where the first arrow is fine, find 3. Now count on from there, right? So like, what's 3 plus 5? A student might go 3, 1, 2, 5, right? They count on from the first student. Okay. No. Okay. Yeah, okay. How are we doing so far? Nothing too trippy? Okay. I want to take, let's do this. Let me think. Yeah, let me go just a little further, and then I'm going to finally shut myself up for a bit. Let's talk about properties of addition. I'm gonna do that one last because these are the ones you normally know. Do you guys remember commutative properties? Does anyone remember? First off, does anyone remember that name? It's okay if you forget what it references. Do you guys remember the name commutative? Does anyone know what the hell it means? Does anyone live at the school? I'm not trying to out anybody. If you live under somewhere, I understand, rough times. We all did what this morning? What's the official word for traveling to this place? Commute. We commuted, yes? Individuals commute. So commutative property says 2 plus 3 plus 5 is the same thing as 2 plus 5 plus 3. You guys with me? Very basic, but again, it's nothing that you're born knowing. Doesn't matter what order you added, basically, is what this is. What actually moved from one side to the other? What changed places? The 5 and the 3. Individual things moved. Just like individuals commute to school, to work. Okay. I try to connect that word to something we all know. Does anyone know what goes with commutative? There's one that normally comes right after that, starts with an A. Do they?
Associative?
Yeah, associative. Associative would be this. Let me just write down the example and then see if anybody picks up on it. That's associative property. What the hell happened? Did any individual number move? Or are they all relatively in the same place? 2, 3, 5. 2, 3, 5. Did any number move? Did any number change order? No. What actually moved? Parentheses moved. Individual things commute. Parentheses associate. So the kind of problem you might see, one kind of problem you might see for me is what identity is this? What property is this? Not identity. What property is this? And I'll have this, you have to name it. Both commutative and associative together just say you can add whatever order you want to. Visually, real quick, before I get too far away, a visual of commutative would be 2 plus 3 is 5, 3 plus 2 is 5, right? So that you can have students not prove it, but at least kind of verify that it makes sense, that it doesn't matter what order you add things in. Ground shaking, I know. What about, here's one that the next two we often forget. Identity we do, but we forget what the hell it means. So identity not in terms of like, you can have your identity stolen, but kind of related to that. It's not just a really good movie with John Cusack in it from a while back. Anyone remember what the identity property is, or what the additive identity is? What is your identity? Name is an aspect of it, right? So your identity is everything that goes into making you, you. If you changed your identity, then you're not you anymore, you're somebody else to some degree. Yes? You're not the same person you used to be. What do I add that maintains the identity of a number, that doesn't change the number? What do you add to not change the number? 0. So 0 is the additive identity. Just to give this away, what would the multiplicative identity be? 1. What do you multiply by to maintain the identity of a number? 1. It's also the loneliest number. No, 1 is the loneliest number. So in this case, a plus 0 equals a. Whoa. Okay. This last one is one that most students really haven't heard of, and it's something called closure. Jeff, can you spell? No, we know this. Has anyone ever heard of the property of closure? Does anyone know what the word closure just means? Has anyone ever had a breakup with somebody? You don't have to tell me about it. Have you ever broken up? Have you ever had a time when you weren't sure what happened and you're like, I need to know what happened? That's you needing closure. Have you ever heard of that phrase? I need closure. Yes? I need to have an end, I need to have a defined end, so I know what this should happen so I can move on. Yes? Okay. You haven't had it happen yet? Great. It's good. It's good. It's not a great thing. So closure in mathematics just says if I add two things, the result is still one of those things. So for example, if I add two whole numbers, can the answer ever be something other than a whole number? Do you see what I mean? So it might be better if I give you a counterexample. If I subtract, now real quick before I say this, what is a whole number again? Do you guys know what a whole number is? What's a whole number? Huh?
Oh no, sorry. Remember not like.
So real quick, the counting numbers are 1, 2, 3. Yes? You with me? 1, 2, 3, 4, 5, 6. Which number looks like a whole? So whole numbers are 0 plus 1, 2, 3. You with me? So whole numbers are 0, 1, 2, 3 forever. You with me? You with me? Now real quick, if I add two whole numbers, ain't no way I'm getting something that is not a whole number. Could I get a fraction if I add two whole numbers? No. Could I get a negative number if I add two whole numbers? No. What if I subtract two whole numbers? What's 7 minus 4? 3. Is that a whole number? Yes. What's 4 minus 7? Negative 3. Is that a whole number? No. Okay, so real quick, I really want you guys to know. I know we're talking about addition, but I thought the idea of closure makes more sense if I show you a counterexample. Whole numbers are not closed under subtraction because when I subtract two whole numbers, I could get a number that's not a whole number. So what I like to think of it as, if we are all the whole numbers there are, if I add any two of us, the answer will be in the room with us. Are you with? Does that make sense? I really want this to make sense because it makes the idea of closure really easy. If we are all the whole numbers, you with me? All the whole numbers in the universe are in this room. If I add two of us together, isn't the answer in this room? So it's closed. I don't have to open the door to go somewhere else. If I subtract two of us, 4 minus 7, do I have to go out the room to get the answer? Do I have to open the door? Yes, so it wouldn't be closed. So to me, that's the beautiful visual for closure. A set is closed under an operation if that operation leads to a number that's in that set. So whole numbers, when I add them, I get a whole number. I don't have to go out the room. Is our whole numbers closed under subtraction? No, because 4 minus 7, for example, ain't in the room of whole numbers. It's outside. It's in the room next door. The freaky ass room that has the negatives. So I'm talking about that room over there. It's got the fractions. We're not talking about that for a while. The room below us has like imaginary numbers, which I understand. I don't know. Anybody who only heard of this idea today, does it make some sense? Are whole numbers closed under multiplication? Can you multiply two whole numbers and get something that's not a whole number? No, of course not. 0 times 8 is 0, 3 times 4 is 12, you know. It's gonna be, are whole numbers closed under division? Hell no. Give me an example. Do it again. 4 divided by 11. Those are two whole numbers. The answer is 4 over 11, which is in that weird ass room over there. Yes? Somebody goes, no. Maybe? All right, I'll stop. I'm sorry. Blah, 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 blah. Okay. Oh, yeah. Oh, okay. Let me shut up for a bit. Here, let me get the kids to show up. I got to stop recording so I don't get a copyright strike. Thank you, YouTube, for wanting to say that phrase. I hear backpacks start going. So let me do it this way, this next little bit. Yeah, okay. Yeah, perfect. How would you approach doing this problem here? If they had, oh shit. You're like, well, Jeff, or we click on a video. Or, sorry. How would you approach this problem here? If you had to do it in your head. Just wait, it'll come back. It'll go away, it'll come back. It'll come back, I said. How would you do that in your head? Does anyone have a good strategy? Some of you guys might be really, really good at doing that in your head, and you're not really doing the strategy, you just kind of visualize. But how can you do that in your head? Anybody have I've given us very specific numbers. Not the 30, not the 40, but the other parts, because
I remember in elementary school they teach you to like stack the numbers and add ones on top of each other.
sure.
So, and then add it over to,
Sure.
yeah.
So listen, the idea of carrying one is actually a huge step for a student. So real quick. All right, I've asked you about Facebook before, I believe. And thank God I don't go there very much. You know, but my mom's on there, she's on there, she's up there. But I go in there sometimes and I'll see, oh, what are these people doing? Why don't they teach them how to add carry the one? Because carrying the one is weird as shit. It is. We all know it. We lived it. We learned a long time ago. These little people, they don't know shit about carry the one. So, yeah, I know what I'm going to do next. Okay, yeah. I was going to do that anyway, but this will be. So, sorry, I'm laying out some stuff. What is 37? Isn't it 30 plus 7? What is 43? It's 40 plus 3. What properties allow me to do the 30 plus 40 first? Yes, associative and commutative. So I can make this 30 plus 40 plus 7 plus 3. Why are 7 and 3 nice? They make 10. And of course 30 and 40 is 70, so this makes 8. Yes? Which is effectively what I do, but I do something called compensation when I do this in my head. What that means is I make this guy pay this guy or vice versa. So for example, if this guy paid this guy 3, he's got 40 and he's got 40, 80. So compensation is kind of like when you get compensated for work, one person loses a little money and you gain a little money, yes? So if I make him lose 3 and him gain 3, 40 and 40 is 80, easy as shit. That is related to realizing 7 and 3 are compatible numbers. So 7 and 3 are what's called compatible numbers. This will actually become a big thing for us in chapter 4. And I already talked about this idea. Another way to do this problem is called compensation, where you basically do this kind of thing in your head. This is called compensation, where 3 goes to 37. So the words we use actually match reality, like the physical reality we live in. Like compensate, one loses, something gains, compatible because they go together, make a nice whole round. I guess so. Now, unfortunately, there's not a lot of situations anymore where you guys actually have to day-to-day add things, subtract things. Even when they get changed, now it's automatic. And I'm like, man, a little tear, because I'm like, that's the only place people were getting any practice with numbers was actually having to calculate the change themselves. Now, I know a lot of people got screwed on that because they would get the wrong change, but anyway, I'll stop. And then, yeah, so for example, something a little more straightforward here. So how would you do this then? 82 plus 41 plus 18. What would you add first? Or, how would you do it? Where are your compatible numbers? 18 and 82, what do they make? 100. And then it's easy from there, right? What properties did I use? Again, associative, and cumulative. So they get used a lot together to move things around. To be really honest, again, both of those properties, they just say you can add whatever order you want to. Right? Because then we're all at the same level of PEMDAS. Yes? Okay, I'm going to say that's enough. That's enough for us today. So we've been through a lot. It was a lot of talking on my part today. Next time, I'm going to do a little more, and then we're going to have like a little group worksheet to work on, the stuff from free. We still got to do, you're not going to believe it, we still got to do multiplication and subtraction. Not in that order. So we'll get into that next time. Okay, thank you.